Okay, so we begin our webinar today. Oh, okay. I think somebody's microphone is not muted. It's Mr. Rizwan. Can you put your mic off? Okay, thank you. And okay, it's okay. So let me start my talk or webinar. So this webinar, as I mentioned, this is basically to give you some information on how a GPS signal looks like. It looks. I suppose that all of you already know GPS and you are using GPS. But if you want to know a little bit more detail inside the signal, so how the signal itself is generated in the satellite. And in some countries now, new systems are coming up, like in India or Korea or Australia, and maybe some other countries, they may be working on that. Or some researchers, they probably would like to know how a signal is created or designed so that they can do some work on that, and pseudolite or indoor GPS or S-bus, or maybe some countries, they might be thinking having their own S-bus satellite system. So you want to do some simulations and all to see the signal characteristics. So this webinar is about 1 hour, and I will show you how a signal is generated in the satellite, not on the receiver side, but on the satellite side. It's more or less similar. And it's to give a very, how to say, the basic overview. We don't go much details on the mathematics. It's just an overview in a very layman language, so it will be easier to understand for many of you. But I suppose that when I look at the registration, I found there are people who already knows and working in a similar field, so it may be very basic for them. But anyway, this is a general purpose webinar to give you the overall overview of the signal. So let me introduce, okay, let me give my brief introduction. So I'm working as an associate professor at the University of Tokyo. So my basic work is related with the GNSS signal design and signal processing, also for indoor or signal authentication, anti-spoofing, interference, jamming, so things like that. But basically it's a signal analysis or related with the signal. So this slide shows that the very basic characteristics of the signal structure. So GPS or other satellites, they have many different types of signals. For example, GPS L1CA, and there is L1C, L2, L5, L6 in QGIS, and also Galileo, they call E1, E5, E6, and IRNSS, they have a L5 and S-band, and Beidou from China, they have a B1, B2, B3, and so many. So there are a lot of signals, but the basic signal is, very basic signal is GPS L1CA, and this is the base for many other satellite systems. Okay. So if you can see here, I put these three headings: carrier, PR and code, and navigation data. So these three are the basic components of the signal. So you must have these three when you generate a signal in the satellite. So you need a carrier, means it's a sine or cosine wave to modulate your other signals, or to carry your signal so that it can travel far away from the antenna to the receiver. So that's the purpose. And this carrier signal will define the frequency of the signal. For example, for GPS, it's L1, means 1575.42 megahertz. So the frequency, this is the frequency. And by this frequency, the carrier signals are defined. And we also name them as L1, L2, L5. We say the L1 band. This is band L1, L2, because it's always difficult to remember these very detailed figures. So we say L1, L2, and L5. When we say L1, it means this frequency, 1575.42. So this is how we address the signals. Then you also need a PRN code. So PRN, it's pseudo random noise. It's called pseudo random noise because it's actually like a random noise, but this signal is very, very important to in a satellite system for navigation or ranging, because without this, you cannot identify the satellite from one satellite to another satellite in the case of GPS and Galileo, Beidou, like that. So they are needed to identify each satellite. And also they should have a very good correlation properties. This I will explain later. But this signal is a must. You must have it. And another purpose of this signal is to calculate the pseudo range distance, the distance from satellite to the receiver. So it helps you to compute the distance between the satellite and the receiver. So this is the purpose to have this signal. But in the case of GLONASS, they have only one type of code for all the satellites. And each satellite is identified by the little bit of different frequencies. So they have a different frequencies, but same code. In the case of GPS, we have a same frequency, but different codes. So there are 32 satellites, so we have 32 codes, but one frequency. So today we basically discuss on the GPS like signal or GPS signal. And we have another data that's called the navigation data. So this is required in the receiver to compute the position of the satellite and some other clock related data or orbit related data. And this is also transmitted from the satellite. So we need carrier, code, and the navigation data. So these three components should be present in a GPS satellite. Okay. So this is a summary of the signal. So if you look at this, this is very, very simple structure: carrier, code, and navigation data. That's all. Only three components. It's very simple, not like other Wi-Fi or communication signals. They have lots of many other different types of signals here. But GPS is very, very simple. And for L1CA, so today we are referring only L1CA, we have this frequency of 1575.42 megahertz. And now this PRN code, the rate, we call the chip rate, means, so how long is this code and what is the transmit rate? That is 1 megahertz, 1.023 megahertz. And this means in terms of time, it will take 1 millisecond to transmit one set of code. Okay. So I will show you in other slides what does this mean. So this PRN code is simply a sequence of zeros and ones, but they are defined by some rule. And we have one set of chips or bits. And this one set has 1023 chips. So these 1023 chips make one set of the code. And this code is transmitted within 1 millisecond from the satellite to the receiver. So every millisecond, you are getting one length of the PRN code coming to the receiver. Okay. So this is what it means. And then we have navigation data, but this navigation data is transmitted at very slow rate. It's only 50 bits per sec. Okay, that means if you convert it 50 bits to time, it will take 20 milliseconds. One bit will take 20 milliseconds to come from the satellite to the receiver. So every 20 milliseconds, you get only one bit. This is very, very slow. And we combine these three signals by doing a modulation called the BPSK. It's called the binary phase shift keying. Like in the radio, you know about AM and FM radio. AM is amplitude modulation, FM is frequency modulation. Okay, like in TV, we have another type of modulation. So this is the same thing, like in radio. For example, you speak. Now your voice is coming from the mouth. This is analog, sort of a signal. And this voice will pick up by the microphone and convert from analog to digital. But it cannot travel from the microphone to another place through the air without we modulate that digital signal with some carrier. Then we combine with the carrier, like in the case of radio, it's FM 80 megahertz, means your carrier frequency is 80 megahertz. In the case of GPS, it's 1575 megahertz. So radio FM is 80 megahertz, means your carrier is 80 megahertz. And you have some signals like the PIN code and other things coming, which is digitized from your voice to the digital signal. So same thing we do in the GPS. So PIN code, carrier, and the navigation data. So these three we have to combine. Now this slide shows you the details of the various signals in GPS. You can see here L1, L2, L5, 3 bands, and their frequencies 1575.42 megahertz, 127.6, 1176.45 megahertz. Okay, so these are the different frequencies you get. And in this frequency, GPS transmits many different types of signals: CA, L1CA, L1C, and L1C has two components called data and pilot channel. So L1C data, L1C pilot. And also there's another signal called P and this bracket Y. This is a military signal which we cannot use. Okay, so we don't care about PY because we can't use. This is for basically for military purpose. So we don't have any access. So it's restricted and it's encrypted. So we don't know how to demodulate this signal and how to use for our purpose. It's not allowed. And for L2, again, we have many different types of signals: CM, CL, and P, military here. And L5, we have I and Q channel. So this IQ is again something like a data and pilot. And if you look at here, look at these frequencies: 1575, 1227, 1176, whatever you take, this is a integer multiple of 10.23 megahertz. This 10.23 megahertz is the clock in the satellite. So this is a base for all the signal generation. So they have a clock in the satellite that will provide 10.23 megahertz of signal, and that will be either amplified or de-amplified to create different types of signals. So that's why it's an integer multiplication of this frequency to have this one 122.7.6, 1176.45, like this for GPS, and also for QGIS. I'm not sure about other satellite systems whether they have the similar thing or not. And this type of design makes the signal generation, the system or hardware, simpler in the satellite. And if you look at here, the chip rate is again, you see 1.023 megahertz, so 1/10 of this clock. So 1 megahertz, 0.5 megahertz, or 10 megahertz. Okay, so something like this. And they have different type of modulation techniques: BPSK, BOK, TM-BOK, and so on. And the data rate, basically it's a 50 or a little bit higher, or in some cases it's a little bit slower, 25 bits per sec. And here, this BPS is bits per sec, and SPS is symbols per second. Means for some signal like L1C here, this data they use the error correction technique. So if they have error correction technique, the rate increases twice with this technique. They call the half FEC. So this bit rate actually increases from 50 to 100. So once it's employed with such error correction technique, so we say SPS, symbols per sec, then we know that, oh, this signal has some error correction technique in the signal. Okay, so this is what it means by BPS or SPS. And now when we look at the actual signal generation in the satellite, so we can refer to this type of interface specification document from US government. And this document is necessary for receiver manufacturers to design their receiver. Otherwise, receiver manufacturers don't know how to make a receiver. So every GPS service provider like a USA, Europe, Japan, China, India, and Russia, they must provide this document. If this document is not available, we cannot make a receiver because we don't know how the signal is coming. Now, this document tells, you can download in internet and tells how to make a signal. Okay. So here you can see how the signals are made. So this seems to be a bit complex, but I will tell you very easy way, because this is the diagram to make both civilian and military signal, CA and P code. This is for P code military, so we forget this part. And this part, goal code generator, is the PRN code generator. I will explain why this is also called goal code. So it's a PRN code generator here. And so we only need this one, and we need the navigation data. And we combine this block and this block to generate the necessary CA code. Okay. And this will be combined with the carrier to transmit from the antenna of the satellite. So this is how the signal is generated. It's very simple here now. Okay, 1 and 1. And here is the P code. This is a bit complex, so we don't care. And we have a clock here. You see this 10.23 megahertz clock. This is the source of the signal to generate all the pulses here. Okay, and this must be very, very accurate, extremely accurate. So in order to keep this accuracy in the satellite, all these satellite systems, GPS, Galileo, GLONASS, whatever, they have atomic clock, rubidium, cesium, or even hydrogen measure clocks. And they have extremely accurate clock. So that's the reason GPS time from GPS signal is used as a reference time for many systems, okay? Because GPS clock is extremely accurate because it's generated using the atomic clocks. And this then 10.23 is the base frequency. And this 10.23 megahertz is either amplified or divided to generate necessary signals here. Okay? So this is how the hardware approach. Okay. So this diagram shows the basics of the signal generation, but this is basically for the hardware, but for software, it's more simpler. Now, this is the way how we generate for the software. Like if you use a MATLAB or some other programming language, so you can generate a carrier at 1575.42 megahertz very simply. It's just either a sine or cosine. You can use a sine. You can simply generate a cosine wave or sine wave using this frequency. But when we generate mathematically, we don't use this frequency. We use some sampling frequency called 16 megahertz or 20 megahertz. And this we generate as a digital signal, and then we upconvert to RF signal at this frequency. So we generate the signal at a lower frequency, say 16 or 20 or 26 megahertz, like that. But we have to generate the CA code at 1 megahertz. Okay, so 1023 chips per millisecond. This code we have to generate, and we have to generate 50 bits of data. Okay, and we combine these two. It's called a spread spectrum, and then we modulate with the carrier like this, and then we upconvert, make an analog signal, and transmit through the antenna. It will be like this. And if you look this signal in the spectrum analyzer, you will see the power of the spectrum like this one. So this is what we'll see later today. And again, this document from the US government or any other service provider, you find this type of document. This will tell you how to generate your PRN code for GPS L1CA. For example, PRN code 1, 2, 3, 4, you see there are 32 GPS satellites, so 1 to 32. So they tell you, this document will tell you how to generate the codes for every satellite. Okay? And there's a detailed explanation, but this document, for some people, may be a little bit difficult to understand. Okay? So I show you easy way. So if some of you are doing the digital communication, so it's very easy for you to understand, but let me explain. You take a 10 bit of registers, so 10 bit. So I count from left to right, bit 1, 2, 3, like this, 10. And you need two registers, 10 bits of registers here. This we call the G1 and G2. And this polynomial, or the taps of these bits, 3 and 10, means we take these 2 bits in the G1 register, and here we take 10 bits, and we have a taps of 2, 3, 6, 8, 9, 10. Okay, we take one every bit from this register, these taps we call the tap, and we do the exclusive OR. And whatever value we get, we put here and shift all the bits to the right. Okay, so this is like this, going on a loop. You do the computation and you shift, you then compute again, you shift. So this is G1 and G2 register, how we do it. I will show you an animation later. But this is same for all 32 satellites, and each satellite is identified by taking one more selection here. For example, for GPS 1, this is a tab called 2 and 7. And for GPS 2, it may be 4 and 8, something like that. Okay, so these two tabs will make different types of codes for different satellites. And this is what we see here. Okay, so which tabs you have to see: 2, 6, 3, 7, 4, 8, like that. Okay, this 2, 6 is telling you that you take 2 and 6 for satellite 1. Okay, that's the meaning. Now I have a video, not a video, but a simulation to show you, animation to show you how this is done. But I don't do this all today, so you can later download the files and you can see yourself. For example, we have two tabs here, and initially they are set with 1, 1, 1, 1, like this. So you see 1, 1, 1, 1, 1, but in the very first case, you always take the last bit of here to as the output of the PIN code. This is 1. And after doing this, then you take these combinations of these 2 bits, 1, 1, 0, 1, 1, 0, and this is after a few steps. So we see here. So for example, now in this case, 0 and 1 exclusive OR is 1. 0 and 1 is 1. And then we take 0, 0, 1 is 1, 1, 1 is 0, 0, 1 is 1, and 1, 1 is 0, 0, 1, 1, 1, 0, sorry, 0, 1 is 1, 1, 1, 0, 0, 1 is 1, 1, 1, 0, 0, 1 is 1. So we do this type of, how to say, the exclusive OR for each of these things. And finally, we take these two taps. 0, 1 is 1, and 1, 0, 1 is the output of this, and this is 1, and this is 1. So 1 and 1 is 0. So we put the third bit output as 0. So if we continue this, we have a sequence of the code, the PIN code. So it's 1, 1, 0, something like this. Okay. Okay. So you see, for PIN code 3, we have this and this 2 taps, but for 25, it's here and here. So by taking different type of taps, you get different types of codes output here. Okay. Now, if you look at these two, so they are completely different, but it looks like a random. So that's the meaning, pseudo random. It's random, but not actually random. It's defined by some rule, like this one. Okay. And this type of generation technique is very, very important. And maybe many of you know the gold code or the linear shift register, this type of random noise. They're important. The reason why we do this is to keep this type of correlation properties. Now, instead of looking at this figure, so I will show you the graph. Now, what I do is, like, I take a PIN code for GPS satellite 1, and also I take the PIN code for GPS satellite 1, but I shift them a little bit. That means the signal is coming from the satellite, and now you are trying to read that signal in your receiver. So the way the receiver works is that the receiver also generates the same signal to get, like uh, if you are going to track PIN code 1 or satellite number 1, you have to generate a replica of the PIN code 1 in your receiver. And then you need to combine these two, or you need to correlate these two to see whether they match or not. So when you correlate, so you don't know what time the signal is transmitted. So there will be some time delay or time lag, and that lag time delay is the pseudo range. But when you match exactly, that means you will get this type of peak, and then you know, okay, I see a peak. That means the receiver knows that PIN code 1 or satellite signal 1 is now present in the signal. If you don't, then the receiver say, okay, satellite 1 is not visible, and it doesn't look for satellite 1. So this is how the receiver works. That means the receiver always does some sort of a correlation. And when we do this type of correlation, so theoretically you get only 4 values. This is a 0, 1 means everything correlate perfectly, or they don't correlate because of noise or because the signal is not present. But theoretically you get either perfect correlation or only 1 bit correlate out of 1023, or either 63 or 65 bits correlate. Otherwise, and the other values are not possible with this type of GPS PIN code. So GPS PIN code is very, very smart design that you won't have other values than these 4 values. Okay? And this value of, this is what we call the cross correlation values of minus 24 dB. And this difference is very, very important if you want to do some interference or jamming type of studies, because you have to know how much power you have to generate to interfere or to jam a GPS receiver. Okay, so I will explain this later in another figure why this 24 dB is very important. Now, when you have a perfect match, you see the signal in that case, like when you put the receiver on, you always see the signal CN0 like a 40 or 50, something like that, means you have this type of peak coming up inside the receiver, because the receivers, they don't display all these intermediate computations because it takes lots of power to do that, so they don't. But if you can do this, you will see this type of peak when you get a signal. When you don't get a signal, you will see something like this. You see here, you see a peak, but here you don't. And in that case, you will have these 3 values, either minus 60 dB, minus 24, or this is almost, 24. So either only 1 chip is correlated, or only 65 chips are correlated. So you have either minus 24 or minus 60 dB of correlation. And this doesn't give you any information, means signal is not present. Okay? So you see something like this. So this is the same thing of this one. So it's just a zoomed like exactly. So we can do this type of simulation in the software, in the MATLAB or some other software, and you can generate 2 PIN codes and do the autocorrelation. And when they are shifted by 1 chip or 1 bit, you can see how much correlation it has. And here you see either the value will be minus 60 dB, minus 24 dB. That means you have 63 bits, 500. This is the delay, and okay, 63 bits of a correlation, but this is only 1 bit of correlation here. So this is what you see in the receiver when it's looking for searching for the GPS satellite. Okay. Now this is just to let you know how these 3 signals, carrier, this is our carrier, and this is code, PIN code, and this is data. How are they combined? Like we have data. This is the navigation data at the 50 BPS, very slow speed. This is 1 megahertz rate, so it's coming much faster than this navigation data. You see, it doesn't change its phase for a long time. but this one is changing the phase much faster because this is 1 megahertz. But this is just to show you the in detail, so it doesn't exactly follow the same rate, 50 or 1 megahertz, just to show you that how this is done. Now, the first case is to combine data and a random code, PN code, and you combine these two. So this is +1, -1. So when you combine these two, so +1 and +1, so the same phase, so they don't change here. But here it changes from +1 to -1. So everything from here, now the phase will be reversed. You see it's here plus, but it goes down to minus. Here is minus, but it goes to plus because this is -1, -1, -1, +1, okay? So the phase reverses. So this is what it means by binary phase shift keying, okay? The phase changes. So this is a modulation technique for GPS. It changes the phase. And then now this signal is combined with the carrier at that has a much higher frequency. And here again, the same thing happens. Now you see the here. Now maybe I will use this one. Now you see here the carrier is coming. So this is the carrier you generate, and then you modulate with this one, okay? So you modulate this spread spectrum, these two combined code with the carrier, and whenever there is a change in phase, you see the carrier also change, okay? Actually, it's like a cycle, okay? This is the normal we generate, then it is modulated with this signal. So instead of going like this, so it goes like this, and here it changes, okay? And this one. So this is the signal you are getting from the antenna, okay? So from the antenna, so we have this type of modulated signal. So this is how the signal actually looks like from the antenna, okay? This is the GPS L1CS signal, very simple data, code, and carrier, and they are all combined together and transmitted from the antenna. Okay. And this one is just like if you need to generate a signal in the simulator, in the software, so you generate a cosine omega t, that is twice the 2 pi f t time. And this f is a center frequency, 1575 megahertz, but we can use a sampling frequency, some other digital IF frequency here. This is a t, this is 1 over sampling frequency, and this is the amplitude. So we can just take a unique unit amplitude. And then you have to generate a PIN code, as I mentioned before, and the details are given in this IS document. And navigation data is quite complex to generate it, and you have to look at the document, and it's very detailed, and we have to generate many different types of navigation data. So this is probably the difficult part, to generate all the bits in the frame. So there are lots of data to be generated, and they define the orbit of the satellite, the clock errors, the clock conditions, and so on. Okay. So if we have these three things together, then we can generate a satellite signal, GPS L1CA. Okay, now I will show you how this is actually generated. So we have a device to convert. So I generate the signal in the computer. That's a digital signal, but this digital signal is converted to analog RF signal using some software radio device, which is nowadays available at very low cost, around $300. So we can use that type of device to generate the RF signal. And then we can use a spectrum analyzer to see whether the signal is properly generated or not. Okay. So this is like this type of device is now available, few $100. I think this is about $400. And this is the software part. So little bit of work here, but the program is available, so you can do it easily. Need to compile and make some modifications. Okay. And this is how the signal looks like. Now I will share another screen to show you this thing in live. So I'm now generating Now in my desk, I'm generating a signal here from my computer, and I'm sending this signal to the spectrum analyzer, and you can see how this actually looks. And then I will show you the importance of this bandwidth, why the PIN code is important, and what does these peaks means, and the value of 24 dB, why it is important for the interference. So before I go to another computer to show this, let me show you some more few slides. Okay, these are okay. So actually, so if you again do the some like if you plot the signal coming to your receiver. Now the satellite, let me show you this one. The satellite is sending the signal. It's about 30 watts. It's very, very weak signal, very small power, 30 watts, okay? And it travels all the way from satellite to the antenna. It's 22,000 or 25,000 kilometer far away. And when it comes, it's extremely low, so low that you can't measure, okay? So this signal, when it arrives to the receiver antenna, so this is the power level, is minus 130 dBm. What does this mean is, like you have a mobile phone or your computer, mouse, radio, any device, you put the power on, you have this level of noise. That's minus 110 dBm. This is the noise you get. Any electronics device, you have this noise for 2 megahertz bandwidth. But GPS is here. It's below the noise. It's hidden inside the noise. Okay, so you can't see, you can't measure. The spectrum analyzers cannot measure this signal unless you make it very strong. Okay, so this is a military signal. That means if you don't tell how to generate a PIN code, it's impossible to detect this signal. Okay, this is the benefit for the military, that you hide everything inside the noise and you broadcast so that you can't see anything. So unless you know how to decode those signals. So for the civilian signal, informations are available, so we can decode because we know how to look at the signal. But for the P code, these are military code, they have encrypted the data, so we don't know how to read the data from P code, so we cannot use it. And we can't measure because it's hidden inside the noise. So this is the technology of the satellite navigation systems. Okay. So this means since it is hidden inside the noise, it's very difficult unless you decode, demodulate, you don't see this peak coming up over the noise. Okay. You have to do that. And without doing this, we can't do anything. And when I talk about that 24 dB of the value, so let me show you this one. You see the power here is minus 130 dBm. Okay, so this is the normal power coming to your receiver antenna. So this is minus 130, but actually it's a little bit stronger, about 5 or 6 dB. So we can say, okay, the power coming to the antenna is between minus 125 to minus 135. Okay, this is the power you get in the receiver, minus 125 to minus 135. And the CA code, the cross correlation properties that I showed you, has a 24 dB of cross correlation. So this means if some interfering or jamming signal is coming, and if that signal is less than 24 dB stronger, means you have a minus 130. And if anything is coming above minus 110, this will totally jam your receiver, okay? Because minus 110 to minus 130 is a 20 dB difference, okay? Means this is now near to your cross correlation property of 22 to 24 dB for the PIN code. So if you have this much of a stronger signal coming to your GPS receiver in the same frequency or nearby frequency, it will totally jam your GPS receiver. If this signal is little bit stronger, say, okay, around 100, 115, it will interfere. The receiver may still work, but it will not work with a good accuracy. Okay? But if it is above this, some signal or noise, it will totally jam your receiver. And if something is around minus 100, then this will totally disrupt your receiver. Nothing works here. Okay? The power is too much, too strong for the receiver to work. So for interference and jamming or spoofing, so these power levels coming to the antenna of the receiver is very, very important. And this is all limited by the mathematics or the design of the signal of the GPS L1CA, the PIN code. But this is very much similar to any other satellite systems because they cannot exceed this total power coming from the satellite because all these are regulated by the ITU. ITU has set the standard for the systems. You cannot exceed this much of power. So they have to reduce the power. And that means the interfering and jamming, they will have a this very much similar effect on any type of GPS signal. So we take GPS L1CS signal as a reference to study all these jamming, interference, or spoofing issues in terms of the power or signal design and all. So maybe some other signal like L1C, it is 2 or 3 dB stronger, but not so much. So this is the point that I would like to highlight why this 24 dB or 22 dB of this cross correlation value is very, very important for the interference issues. Now I will switch to another computer to show you the actual thing. Okay, so I suppose that now you can see the signal coming to the spectrum analyzer. I have used a Tektronix spectrum analyzer. So this is a small device that can connect to the computer. And this spectrum analyzer, now the signal is fed from the GPS, the software device that I have. It's directly connected to the spectrum analyzer, not from the antenna, because you cannot transmit from the antenna, it's illegal. You cannot transmit in the air, otherwise it will interfere the nearby devices. So you have to be very careful when you do this type of test. So you have to connect from the cable of your transmitter to the device. And now I am sending the signal here. So this is how, if you look at the satellite, at the antenna, the signal will be like this. Okay, it has a carrier, code, and data. All they are modulated and they are transmitted. Now this is the peak power I'm sending, and this is the average because there is modulation and all. And you see the bandwidth is here is a 1575.42 megahertz, and then it's a 2 megahertz bandwidth here. So we can send maybe I can put a very small 5 megahertz bandwidth. I can zoom it. So here is the center. So from here to now here is a 5 megahertz. So span is 5. So this is 1 megahertz. Okay, 1.5 and 2 and 2.5. So 2.5 here, 2.5 here. So if you look this peak, okay, this is a 1 megahertz. You see two grids. So these two grids from here to here is 1 meg. So 1 meg, 1 meg. So this is a 2 megahertz main lobe. Then we have the side lobe. We call the main lobe and the side lobe. And this main lobe will have more than 90% of the power transmitted from the satellite. For GPS L1CA, this bandwidth, PIN code bandwidth is 2 megahertz. And when you design the receiver, so your receiver bandwidth must be larger than this one to get all the power transmitted by the satellite. So you need probably at least 4 megahertz of bandwidth in the receiver so that you can cover from here to here. So, and this will cover maybe more than 99% of the power transmitted by the antenna to your receiver. Okay. The wider the bandwidth, the better it is. But also if the bandwidth is too wide, you also get other noises that you can see here. So I made 10 megahertz. Okay. So all these noises will also enter, but the receiver will again do some filtering. So it may not be a problem, but it depends on the design. And today the receivers are not only for L1CA, it has capability to receive many other signals as well that have a different type of signal structures. Some has a 2 megahertz bandwidth, some has a 4 megahertz, and some Galileo signal, they have a 20 megahertz of bandwidth, very, very large bandwidth signals. So because of the bulk modulation. So the receiver design is very complex and they really need different types of filtering techniques. But for GPS L1 CA is a very simple, very small bandwidth, but very nicely designed. So the receiver design is very, very simple. And that's one of the reasons why the GPS receiver L1 receiver chipsets are very, very cheap as well, because the design is simple, receiver is simple, and that means lower cost and so on. Okay. Now, I can change many things here actually. So I'm continuously sending the signal. So we can send some like a power. We can change the power here. I have put maybe put 20 dB. So if I increase the attenuation by 10 dB, this power should go down by 10 dB. Okay, you see now this decreased by 10 dB. Or we can increase it. So I can change to 10. So it increases. And so we can change many things here. So we can even change the frequency. Like, so if you want to do some interference or that type of jamming, so now I'm generating this at the GPS. So I want to change this to a little bit of, okay, I want to make offset of 5 megahertz to do some test. Okay. Oh, no, this is not yet 0. Okay, I send 1570. Now you see my center frequency I have set here, shift here. Let me make, just change the bandwidth. Okay, you see, before it was here, 1575. Now I made a 5 megahertz offset and it moved here. So this type of things we can do using this type of software radio, and you can generate and you can do the test, but be careful, don't transmit the signal in the air. Okay? This may interfere other devices. So this software or hardware, software is available, hardware is available. So if your research or your work is related with interference jamming, signal design, or some signal analysis, these tools will be very, very useful. Now let me just go to 4.2, go back to the original. Okay. Oh, I don't know what happened. So maybe because I'm changing many things. So, okay, it get a little bit, it went to somewhere. So, okay. Now I stop here. So this is how the GPS L1 CS signal looks like. And so you can use this type of tool, but unfortunately, this Tektronix device is not so cheap. It's a bit expensive. I don't know the market price. It varies a lot in country to country. It costs around maybe around $5,000, $3,000 to $5,000, at least $3,000. So it goes up to $5,000. So, but the signal generator, this one, so you can buy much cheaper, around $300 to $500. So you can do some analysis. And this device that I'm using to generate the GPS signal can also be used as a spectrum analyzer, not up to this level of quality, but you can still do this type of spectrum measurement and all. So it's possible to do this. Okay, so this is all about my presentation. So let me know some questions what you have. I see. Okay, so let me take a few questions if you have. And please, you can check this video later. I will save it and upload to YouTube so you can listen again. And also this PowerPoint file, I will send you by email to all the registered participants. And after a week later, you can also download from our university website. So now I can't go to the university because of COVID here. So I can't access the website to update, but I plan to go next week and I will upload so that you can download also from the university website. But anyway, you will get the PDF file from through your email. I suppose the file size is not a big problem. Okay, so that's all from my side. So please send me your questions or ask me. You can put your mic on. And please don't forget to send your feedback, okay? And that's very important. So somebody asks, what is the name of this signal generator? So, okay, so this is the what we call the blade RF. It's the blade RF. Blade RF. We use a blade RF. Okay, so you can buy it online in internet, Amazon, or it costs around $400 or something like that, $500. Also, you can buy a very cheap $15 or $20 what's that called, $20 USB stick to do this type of spectrum analyzer. I don't remember the name, but I can check that for you and send information later. Okay, any other questions? Oh, let me see, there's many chats here. How okay, what happened on the signal if we transmit two PRN at the same time? It's okay. Because we combine all those PRNs. So actually the signal generator, the one I'm transmitting here, it's not only one PRN. It's many signals here. Oh, I need to restart this device. It takes some time, but anyway. So the signal you see here, this is not only one PN code. It's a combination of, I think 10 or 12 visible satellites, okay? So we can combine all. So you can do that, no problem. Or you can just send one, or you can combine all of them. But there's a way to how to combine them. For GPS L1CA, it's very, very simple. But for other signals like a Galileo, when they have a bulk, it's very complex. So, but if you want to know all these signal combinations and for other complex things, we have to do more webinars in future. But I am also not a very expert on those bulk or complex signals. So probably we have to invite somebody who knows very well on that, because those Galileo bulk signals are very complex. It's not as simple like GPS L1CA. But before doing that, we have to know how to do for GPS L1CA to understand practically how we can generate. It's the simplest one. So somebody asks, what board are you using to generate? Yeah, that's Blade RF. That's what I replied. Is there any open source tools available to analyze GPS signals after collecting GPS data? Yes, there you can download some MATLAB source, but you need a front end. So you have to probably write your own software receiver. So at least you have to write some codes to do the signal acquisition. And when you need to do signal acquisition, you must know how to generate the PRN code. So please try generation of the PRN code yourself. I have a very detailed this handout, so I can upload this later. You can see and try. Yes, RTL, SDR, yes, we can use that. Yes, this is what I am saying, RTL, SDR. So this RTL, SDR is very cheap, around $15. It's not that good, but you can still use it. So you can see this type of spectrum. And I use this a lot to carry, I mean, when I go outside, so it's much easier. Because to carry this Tektronix is not, it's portable, but it's very expensive and it's not so easy, okay, to carry with these things when you go abroad, especially. So customs and a big problem. So RTL SDR is quite good, and also you can record RF signal in RTL SDR, and that's just yeah, around $25. So with the $25, you get quite a good one, but I think normally it's around $12. Yes, signal specification document for QGIS is also available. So please download from the QGIS website. You can search QGIS interface specification document. So all the details are given. So every service provider, they have this document. So any other, can we say that 10.23 megahertz is a fundamental frequency? Yes, that's the fundamental frequency, yes. For satellite-based system, I mean navigation satellites. You see all these multiplication 1.5, the frequency bandwidth, they are integer multiplication of 10.23. How can you use pseudo-random noise on a spectrum analyzer? So I don't understand this question. What does it mean? How can you see pseudo? Yeah, spectrum analyzer is the Fourier transformation. Okay, so what we are looking here is not the time domain; it's the frequency domain. So if you want to see the time domain, you need not the spectrum analyzer, you need the oscilloscope. You see the in the time domain, then you can see the PN code. But you cannot see this. Now, if you connect the antenna, GPS antenna to your spectrum analyzer, you don't see like this, because I show you that the signal coming to the antenna is minus 110 dBm. And that minus 130 is well below the thermal noise of minus 110. So it's hidden inside the noise. So you can't see any GPS signal using the spectrum analyzer. But there are some spectrum analyzer which can measure up to minus 160. Okay? But it's quite expensive, but it's available. But still you see just a very small peak somewhere over here. All the noise and little bit of balls over the frequency. But you don't see very clear like this one. So if you really want to see that type of a signal coming up like this, what you have to put is a very high gain dish antenna on the rooftop that has a gain of above 20 or 30 dB, around 20 dB at least. So you will have from minus 130. So you have to come above the noise floor, that's minus 110. So you need at least 25 dB of gain. So you get the signal above 110. So you get a dish antenna of big antenna, about 30 dB of gain, and you capture the GPS signal. Then you can see, then you can measure using a normal spectrum analyzer, and you can see something like this. Yes, impedance is 50 ohm, yes. So okay, so any further questions? Okay, if not, I would like to stop here, and please send your feedback. I send you the link from PTX to your email. And we plan to do this type of webinar maybe almost once in 2 weeks, or based on the demand, or maybe every week even. So it's probably at least once in every 2 weeks, but we plan to cover technical topics like this, also applications and some basic topics and some special applications or special topics as per request. Or we want to know what you do in your region, in your country, what type of applications, how you use, and what problems you have, and how to solve those things. So it's in how to say, the very general types of discussions also we want to do sometimes. Okay, so thank you very much. I would like to stop here and hope to see you in the next webinar. You will get the PDF file after some time, and also you will see the video maybe tomorrow, or let me see. So thank you very much, and hope to see you in the next webinar. And please don't forget to send your feedback, okay? And please take care of COVID. So